In the previous video, we had discussed about the postulates of the Bohr's atomic theory or the Bohr's model of the atom. In this video, we're going to be specifically talking about Bohr's model of the atom for hydrogen. So, according to the Bohr's theory Bohr's theory for hydrogen atom, first point, the stationary states for electrons are numbered 1, 2, 3, and these are called as the principal quantum numbers. So the stationary states, that is, in the previous while we were talking about postulates, I told you that you have the energy levels, and these orbits are also called as the stationary states. And they have been numbered as 1, 2, 3, 4, and this is also called as the principal quantum number. The second uh, point is the radii of the stationary states are expressed as Rn equals to n square A naught. So A naught is 52.5 picometers. So when n is 1, that is, for the first stationary state or the first orbit, the radius is 52.9 picometers. So as the value of n changes, the radius will also change. So the electron of the hydrogen atom is usually found when in the first shell, that is when n equals to 1. But as the value of the n increases, the radius will also increase. So electron will be farther from the nucleus as the value of n increases. So if the value of n was 2, obviously there would be a difference. It would be higher than 52.9. So this means that as there is an increase in the value of n, the radius of that particular, of where that particular electron present is also going to increase. Excuse me, I'm so sorry. The next one is the energy of the stationary state. The stationary state is basically your orbit. So it is given by En equals to minus RH by 1 by n squared. N is our orbit, that is 1, 2, 3. That's the principal quantum number. And RH is the Rydberg constant. If you remember, we had spoken about RH, this Rydberg constant, when we had the equation, when we had the Balmer series, all of those series, when they were compiled, we had the Rydberg equation, and R was the Rydberg constant over there. That is different from this. Okay, R and RH are different from each other. Both of them are called Rydberg constant, but that is in centimeter inverse, whereas RH is 2.18 into 10 to the power minus 18 joules. So when n equals, this is because I just want to point out this because you shouldn't get confused between the two terms. So when n equals to 1, the value of E, the energy of that particular stationary state, is minus 2.18 into 10 to the power minus 18 joules. And when n equals to 2, it's 0.545 into 10 to the power minus 18 joules. So when there is an increase in the value of n, the energy of the stationary state is decreasing. So this is the energy level diagram that represents the various stationary states. Now, the energy of, so as we notice over here, the energy of the hydrogen atom is negative. This means the energy of the atom is less than the energy of a free electron at rest. When a free electron is far enough from the nucleus, its energy almost becomes zero. And so this particular electron is considered not to be influenced by the nucleus, but there is the thing is, even if it is far away, it is said that there will be some amount of influence of the nucleus on the electron. So the negative sign that is present in front of the energy is the electron is bound to the nucleus and it is unstable than that the one in which it is far away. So the negative sign over here just shows the stability of the particular electron. The fourth one, Bohr's theory can also be applied to ions that contain only one electron. So all these ions that we have, He plus, helium plus, lithium plus 2, beryllium plus 3, all of these have only one electron. So the equation which we have there can also be applied to such systems. But here we will also be considering the atomic number, that is Z. So this and so that equation, so En equals to minus RH into 1 by n square is the equation we learned as the energy for stationary phase state, and Rn equals to n square into A naught. So the same equation can be applied over here. Here, instead of writing RH, we have written the value of the Rydberg constant. So minus 2.18 into 10 to the power minus 18. And instead of 1 by n square, you have z square by n square because we are considering the atomic number. And radii is given as you remember, we just have n square into A naught. A naught is 52.9 picometers. So we're just substituting, and here you also have the atomic number being considered. Notice it is very important for us to remember that it's only for one electron systems. We are not talking about systems where, suppose let's take helium, if it had He, if it had been He instead of He plus, then it has two electrons in the system. So these equations will not be applicable for such systems. Last one, it is possible to calculate the velocities of the electrons moving in the orbits. So that particular thing is not something we're discussing over here. You'll be learning it probably at later stages. So qualitatively, we can calculate the magnitude of the magnitude of velocity of the electron. And it increases with increase in positive charge on the nucleus and decreases with decrease of principal quantum number. So the mathematical equations will not be done right now. You just need to remember that the magnitude of velocity of the electron increases with increase in positive charge on the nucleus, and it decreases with decrease in the decreases with increase of the principal quantum number. In essence, the velocity, first of all, is decreasing with increase in the principal quantum number, means that if the electron is in the outermost orbit, its velocity will be relatively less compared to the one which is closer to the nucleus. The second one is that it increases with increase in positive charge. So as the positive charge increases, the velocity of the electron also increases. With that, we finish the Bohr's atomic theory for the hydrogen atom. In the next video, I think we will be going back to the line spectrum of hydrogen and understanding Bohr's perspective. If you haven't, you have to do check out the video which I did on the basic understanding or the basic level understanding about the line spectra of hydrogen atom.